Okay, so we are talking about log function attributes and transformations. We've already talked about natural log, right? You remember Alin, that guy from last week? Natural log and log are brothers. They're the same thing, right? So it's gonna go kind of quickly. We're just building on from it. Does that make sense? All right. So 3A.4, here we go. Up first, we are going to talk about when your base equals 2, okay? Your basic equaling 2 is one of the most utilized log functions, and that's just because multiples of 2, powers of 2 are used a lot in situations, right? Things double a lot, and yeah. How does that look like as a function? So as a function, it would be f of x equals log base 2 of x, okay? That's what it's looking like. When you have log base 2 of x, this is the graph that is produced from it. Yes, do we see the graph? Okay. From this graph, at this point in Algebra 2, you should be able to tell me what's the domain, the range, the intercepts, correct? Without a problem. Yeah? All right. So, starting off, what is my domain? Where does my graph start at? 0 to infinity. We start at 0 and we continue to infinity. Do we ever cross 0? No, because we do not cross 0. Notice that I did not put a bracket. I put a parenthesis. And that's because x is greater than 0, not greater than or equal to 0. Yes? Okay. My range, bottom to top, what is taking place? All real numbers. So we're all real numbers, which means that we go from negative infinity to positive infinity. Correct? Parentheses, parentheses, parentheses. Oh, okay. Yeah, everything's parentheses. You can never use brackets on infinity. You can't contain something that goes on forever.
Wait, no, I thought you would put it on the other side of the
Here? Yeah, that's why it's the parenthesis. We're not passing 0 and we don't equal to 0. Bracket would mean that I equal 0 and I do not equal.
Why did they put the bracket in the
That's if I'm equal to that value. Like if I start there. Yes, if it's greater than or equal to, it's going to be a bracket. That's why I said this is when you are strictly greater than, which is why it's double parenthesis. Okay. All right. Intercept, x or y. Which one do I have? I have an x, and where is it at? 1. Agreed? Okay. Asymptote. Asymptote is your boundary line. Where's my boundary for this function? It's vertical, so it's a vertical boundary, and it's at what? At x equals 0. That's my invisible boundary line, my asymptote, that says this is where you stop at. Do not move. You can't go any further. Okay? From left to right, is this function increasing or decreasing? It's increasing, and we say that. So when we're describing whether something's increasing or decreasing, we would write as x goes to infinity, our f of x is also going to infinity, right? So as our x's grows, so are our y's. That's the definition of increasing. Make sense? All right, so with that same knowledge really quick, you're going to fill in the attributes for the common log, which is what's up next. So here, this is called our common log. Okay, common log means that it's the function that's just, when you see a log by itself, that means that your b equals 10. Okay, the common log means that your b is automatically 10. Okay, so what do you notice about the attributes of the common log? They are the same. Oh my gosh, they're exactly the same. The domain is still 0 to infinity. Your range is still negative infinity to positive infinity. Your intercept is still at 1, 0. You still have a vertical asymptote at x equals 0, and the graph is still doing what? Increasing. As our x's grows, so do our y's. Got my infinity. Okay. That's because all log functions in their basic form. Okay. Basic form means no left, right, up, or down, right? That's a log in its basic form. They're going to have all of the same properties. Okay. And we're going to model that, practice, show some of that in Desmos. Other thing I want to point out here is that if you look between the two functions here, when we're at 2, it is 1, and 2 is our base, right? Notice here, when we're on the common log, I go to 10, and 10 is 1, and 10 is our what? Our base, okay? Your output of 1 lets you know what your base is of your log. It'll be what? 20 what? No. No, it'll be 100, 100, comma 2. 10 to the second power.
Oh,
Remember, logs and exponentials are powers. Yeah.
So why would, for the first one, why would it be equal to the base?
Our log, our b equals 2. So it told us b equal 2, and that's why our base is 2. But we know from the graph that the value that our 1's at lets us know our base. All right, we're going to go to Desmos and do a little bit of a discovery thing. So with your, you should have your Desmos open like I instructed you before we got started. So on Desmo graphs, it allows you to put in your different bases. When you're putting in the different bases on Desmo's graph, you're going to type log. And you're going to hit shift dash. The dash key is next to your 0. So shift dash, and you can type in whatever base you need. Yes?
I wonder how it could do that, like, a long time ago. Yeah, I was like,
All right. So notice I put in log base 10. For common log, I just have to type log x, because it's already implied that your base is 10. Yes? Okay. So when I look at both graphs, notice that they both are at 1, 0. The value of the red, it has 2, 1. Kind of hard to make it there. We have 2, 1. The value of the 10 is also, let me get there. It's there. Now, this is where it gets annoying. You're like, I can't see it. Well, we're going to turn on the tables to see it. So to turn on your table, you go to the box that you're in and you're going to press the gear. The gear's like, what do you want? And I'm like, I want my table. And it will show me the values of my table. It only shows you from -2 to 2. Everything else you have to input yourself. Does that make sense? So my next value of 2 would be 4, and that's because you're counting by multiples of 2s. Does that make sense? 2 to, okay, so again, for the table, we click on that. You click on there, and then I can continue. 2 times 2 is going to be 4. 4 times 2 is going to be 8. 8 times 2 is going to be 16, and I can see the rest of my values. Do we see that? Okay, because your log is that your x's are what's being multiplied. Does that make sense? Yeah? Okay, let's do it with our 10s. So again, I'm going to turn on the table. I press the gear, open the table, and now we're going to count by 10s. So 1 times 10 is 10. 10 times 10 is 10 times 10 is 100. 100 times 10 is 1,000. So those would be the smallest whole values of the 10s. Does that make sense? Yeah? Okay. If my base changed, so right now we're counting by 10s. If my base changes, it's going to change what my x's are counting by. Does that make sense? Okay. Now, notice again, your y values are the same. Do you see that? Exactly. I'll be multiples of 3, right? So my base went from 2, I can spell, to 3. You want to do 7?
No, 4. No.
Okay, I don't really care what you
5.
type in. 7s aren't easy to count by. We
5.
could do 4. If we switch to 4, that means that this also has to change. You either can manually change it or close it and then just reopen it. I just close and reopen it because I don't want to manually change anything. And now we're counting by 4s. So 1 times 4 is 4. 4 times 4 is 16. You have to manually change it. Like did you change your 4 here? Did you click on the box? You sure?
You gotta exit and then reopen it. I did.
I'll come and look. I don't know what you did. And then we have 64. Are we seeing the table patterns? Are we seeing the changes? Okay. Take a moment, change it, get used to it, manipulate it.
I'll just send a picture.
It's not wrong. It was just it only had.
It's not working.
Yeah, you have to change it.
Like we just changed it.
Like you
Yeah. Like the whole thing.
Okay, 1 times 4 is 4. 4 times 4 is. I said it. It's recorded.
Let's see. You can pick.
I don't know how I made an extra class. Do we have an assignment? But I made an extra. I need that assignment thing.
It's online. All right, here we go. Are we good? Are we comfortable with putting logs into the Desmos and manipulating the tables and using the tables?
Yeah.
Yes, no, maybe so. Yeah? All right. Back to our paper. Okay. So log transformations. Now, what we just did with Desmos and the patterns we represented are before any transformations take place. Yes? Was I adding, subtracting, or multiplying by anything when I was doing any of those? No, I was not. Okay. When you have transformations, things are going to change. It's called transformations. It's not going to be the parent function anymore. It's going to be the transformed view of that. Okay. So when we put it all together, all of our transformations look like this. F of x equals a log base b of x minus c plus d, right? Will I have all of them at once all the time? No, I will not, but I could possibly, right? Your A, your B, your A, your C, and your D are doing the same things that they've done for all the other functions. Our G is going to make us go up and down, right? Our C, what do we got to remember about our C? X's are liars. X's lie. Okay? It looks like it's going to go to the left, but it's actually going to the right. It's always the opposite of what it's doing. Up and down is your D. Your C is your left and your right. Okay? And your A is your stretch, compress, or reflection. If A is less than 0, that means that it is negative. And if you have a negative, you're going to end up reflecting. Did those rules change? Not at all. Okay? So we're going to practice applying those 2 rules or applying a rule, 2 of the rules and going from there. Yes? So we're going to do it manually because we're smart and we got big brains. We're going to do it manually. So up first, we have, it says graph and label the parent function y base 2 of x and its transformations. Y equals log base 2 of x plus 4. Y equals log base 2x plus 4. So this is my parent function. This is the PC, the parent function. Correct? So for our parent function from our table that we drew in, stop it, pin, that we drew in Desmos, we learned that we're at 1, 0, correct? We're at 2, 1, and we had a 4, 2. Yes? No one's like, you made that up, miss. Okay, so we're going to draw on our parent function. Remember, these are the straightest lines you've ever seen in your life. I know. They're beautiful. Thank you for your acceptance. So putting our parent function first, I'm going to go and draw. So I'm at 1, 0, 2, 1, and I'm at 4, 2. Yes? PC done. PF done. I don't know why I wrote PC. That's calculus. PF Parent function. All right, we're now going to do our first transformation. We're going to call this y1. Looking at y1, what is it telling me to do to my parent function? I'm going to do what? I'm going to go left 4 units. So left 4 units, right? So that's saying I'm going to take the points that I have, pew, 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 and my asymptote, and we're moving everybody to the left. Yes? All right, here we go. 1, 2, 3, 4. So my asymptote is now at -4. Now I'm going to take my y-intercept. They may not be letting people know right now. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. And I can't draw. It's going to be the most curvaceous thing you've seen in a while. I know. And there's my y1. Did we shift it to the left? Was that terrible?
No.
Okay. Now we're going to do our y2. What is it y2 asking of us? Says do what? There we go. We're going to go up 4 units. So we're going to take our parent function values. Boom, boom, boom. And we're going to shift everybody up 4 units. Make sense? So we're going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Does that affect my asymptote? No. Asymptotes are only affected when you go left and right.
I think you did that. Yeah, you did. It's supposed to be the last one.
No, because I lowered my x-axis, ma'am. Don't tell me I know what I did.
I was just trying to tell you.
Yeah. Big brain. Sometimes. Okay. I know my limits. All right. So looking at this, a conclusion that we can be made is that which of our transformation rules controls our asymptote? Is it our A, our C, or our D? Our C. So if we have a C, that's going to affect our asymptote, right? So keeping that in mind when you are analyzing graphs. All right. So the domain, what is the domain then of our y1? It now starts where? Where does the purple start on me? We now start at -4 and then we go to infinity, right? Was the domain of the green affected? No, just the domain of the purple. Yes. All right. Up next is going backwards. If I give you a graph and I say identify the parent function and then identify the transformation, there are things that you want to look at. You want to look at what is your value for y equals 1, because that tells us our b, our base, right? And then from there, how did the graphs change? Okay, so starting off with what we have, looking at that's what I'm asking you. Which is our parent function? The red or the blue? The red. Parent functions are increasing functions. If you look back at the first 2 models we did, were they not both increasing functions? With vertical asymptotes at 0. So the red, this is our y1. That is our parent function. And what is the base of it? 3, because remember your base is where your y is equal to 1. So we know that y1 equals log base 3 of x. What is the transformation from the red to the blue? A reflection. How do I make it a reflection? It has to be a negative. Your A has to be negative. So it's going to be negative log 3 of x. Does that make sense? And that's because from here to here, we reflected over the x-axis. In order to reflect over the x-axis, your A value has to be negative. Agree? All right. Next is moving on to word problems. Word problems. Okay. It's actually not that bad. All right. The profits in dollars from subscription to a local newspaper are shown by the formula P of X equals negative K plus 60 log 10 of X, where X is the number of subscriptions sold and K is a constant. Find K if the newspaper makes a profit of $35 from selling 100 subscription. Okay. So the first thing we need to identify is our independent and dependent, our X and our Y. What is our X value that's given to us? Our X value is 100. Because it says X is the number of subscriptions. Do we see that? So therefore, 100 subscriptions is our X value. What is our output? Our 35. So this is our profit, our P of X, our output, our Y value. Right? So I'm going to plug in what I know and solve for what I don't know. Agree? So we're going to plug in. We have 35 equals negative K plus 60 times the log. Do I have to write the 10? I do not have to write 10. Log of 100. Okay, we have the skills to solve this without a calculator. So we're going to model it without a calculator, and then we will emphasize modeling it graphically. Okay, so without a calculator, log 100 is asking you 10 to what power equals 100. Do you remember that? Mm-hmm. So what is log of 100? 2. So we have negative K plus 60 times 2, because that's what log of 100 is asking. 10 to what power equals 100? And the answer is, I don't know. You see nothing.
Okay.
You are going crazy. Okay. And now, is this just a basic algebra 1 problem to solve? Yeah. It really is. So what do? What's 60 times 2? 120. I'm going to have to move it. So how do I move it? So I'm going to subtract 120 from both sides. When I subtract 120 from both sides, what do I get? 60 times 2 is 120. We get what? 8 equals negative K. So what is K? 85. So K equals 85. So now we know the K value. That's it.
All right, don't go no further. No, it's just.
Okay. Again, word problems are our friends. We freak out, but they're not terrible. Yes? Perhaps. All right. They would have to in order for you to solve an unknown. You wouldn't have enough information. All right, next, max and mins. So max and mins, in your notes, you have the review of natural log, right? It reminds you what natural log is. We've already talked about it. I put it in there just so you can have it all together with log, okay? The reason being is that log base E is the same thing as natural log. Do you remember that from our last unit, okay? Now, natural log functions, or all log functions, are increasing in their standard form, right? Because the functions are increasing, when you're defining your max and your max and min are going to be based off of the interval given to you. So if it says identify your max and min on this interval from E to 10, well, this has to be my max, right? Because as my function grows, what happens to my values? They grow. Does that make sense? And this has to be my min on the back. I said the other parts are just review from your other stuff. So if I'm going to find the max and min value, I'm going to plug these in to identify. So my max value equals f of 10. F of 10 is the natural log of 10. That's my exact max value. My min value is going to equal f of e, which is natural log of e. Does anyone remember what the natural log of e is?
What?
Good job.
Oh, wait. I'm so smart.
You are.
Right.
Okay. So again, the reason why this is because this function is doing what from left to right? increasing. If it wasn't increasing, it would be the opposite. Does that make sense? So when it asks you to identify your max and min values over an interval, if it's an increasing interval, your min's going to come from your smallest x, your max is going to come from your largest x, because it's increasing over that interval. All right. All right. Sadly, we did not get to our exit ticket. So you're flying solo on that guy. But it's 3 questions analyzing the log function. Thank you for a great day. And yeah.